This time we have a cylinder. So looking in that cylinder, let's see, we have, here's our cylinder. I noticed that the cylinder, of course, has symmetry around the z-axis. And so to parametrize this, we could probably use cylindrical coordinates as a way to naturally get a parametrization. Remember, in cylindrical, x is r cosine theta, and y is r sine theta, and z is z. But looking at our equation, in cylindrical, x squared plus y squared is r squared cosine squared plus r squared sine squared. That's r squared. So really the equation of this in cylindrical is r squared minus z squared over 3 equals 0. I can see that as z goes from the bottom to the top, the r value is always a function of what your z value is. So I could even solve for it, right? The radius is z over root 3. Knowing that, I can take that equation in cylindrical and convert it into a parametrization. See, my x is going to be r, which is 1 over root 3 z times cosine theta, and y is 1 over root 3 z, that's r, times sine theta, and the z can just play itself. So you see how I have my location x, y, and z as a function of two things, z and theta. Now I need bounds on those, so I want to make sure I look all the way around. So if I only want to look all the way around once, I could let theta go from 0 to 2 pi. Now, to get bounds on z, I have to consider that I need this to lie within the cylinder of radius 2. So I want this part to lie within the cylinder of radius 2. That means there's got to be a lower cutoff on z and an upper cutoff on z. Well, if x squared plus y squared equals 4, that says that z squared, let's see, z squared over 3, right, equals 4 from this equation and this equation together. So that says z squared equals 12, so z equals plus or minus 2 root 3. So I've got where the cone goes outside of the cylinder, that occurs when z is either negative 2 root 3 or positive 2 root 3. So now we have our location x, y, and z given in terms of two parameters, theta and z. Now since we've got Maple, we might as well plot this to kind of see how it's working. So if we put in our equations here, do plot 3D, and this is a parameterization, so we can put in our three functions. Let's see, z times cosine theta over the square root of 3, that's my x-coordinate, and z times the sine of theta over the square root of 3 is my y-coordinate, and my z-coordinate is just z. Now I can put in my bounds on theta and z. So we have theta goes from 0 to 2 pi, and z goes from negative 2 times the square root of 3 up to 2 times the square root of 3. Let's see, I need a times sign between these two. See if I've got it. Okay, yeah, we did it. Here's our parametrization of our cone here. Now the scaling is a little bit messed up here. Let's do projection equal constrained, and that will force it to have the correct shape. Otherwise, Maple just kind of rescales everything so that it fits nicely in the box. We could blow this up a little bit though to get a look at the cone that we created. We did a nice job of parametrizing our cone. Let's go back though and do this again. You'll remember in spherical coordinates, cones have pretty simple representations as well. As for a cone, basically, remember in spherical we gave our position as rho, which was a distance from the origin, with a tip-out angle phi, so the angle that we made with the positive z-axis, and then we had the angle that we made with the shadow of the point makes with the positive x-axis, that's theta. So remember that in spherical, x is rho sine phi cosine theta. The y value comes from rho sine phi sine theta, and the z value comes from rho cosine phi. Now for a cone, if you look at that cone, the tip-out angle is always the same. So the equation of a cone is that phi equals a constant. We just need to figure out what that constant is. Well, let's look at our equation for a given value of r. So we have a value of r here, and then we have our value of z, and then our tip-out angle phi is right here. But what we know from our equation is that r squared equals z squared over 3. So that means that if we just take the positive value for r is z over the square root of 3. Now, the tangent of phi would be the opposite over the adjacent, which would be r over z. So that would be z over root 3 over z, which would be 1 over root 3. Well, what angle has a tangent that's 1 over root 3? That angle is pi 6, right? So phi equals pi 6. That's one value you could use for phi. So we found out the constant now by considering sort of the cross-section. You can imagine just sort of looking at a cross-section of our cone. Then we have this triangle. It was from that triangle that we figured out that the tangent was 1 over root 3, and that from there we figured out our angle phi. So that gives us equations that would parametrize our cone. X is rho sine phi, but the sine of pi 6 is 1/2, so we have rho times 1/2 cosine theta. And y is rho sine phi, which is again 1/2 times sine theta. And z is equal to rho cos phi, but the cosine of pi 6 is root 3 over 2. So this creates a parametrization. We need bounds on rho. So we're going to find bounds on rho. Also bounds on theta. The bounds on theta are easy. Theta goes from 0 to 2 pi. What about bounds on rho? Well, rho is the distance that we can go out, right? And if we have to stay inside a cylinder of radius 2, let's see, that puts bounds on rho then, because r, the biggest rho can be occurs when r equals 2, right? But when r equals 2, then we know that from this equation that z is root 3r. So the z value is root 3 times 2. And the rho value, since this is a right triangle here, the rho value is the square root of r squared plus z squared. So that would be the square root of 4 plus, if you square 2 root 3 times 2, if you square root 3 times 2, you get 12. So we get the square root of 16, which is 4. So we have now bounds on rho. Rho goes from, well, if we let rho go from 0 to 4, we'll always be in the upper part of the cone, because we're only allowed to tip out so far. But if we let rho go from -4 to 4, then that will create the entire cone. Let's put that parametrization into Maple and see what we get. So we've got, let's make some space down here. We want to do plot 3D. Plot 3D, and our equations are rho times cosine theta. I want half of that. And rho times the sine of theta. I want half of that. And the z was square root of 3 times rho all over 2. And then we just need to put bounds on rho. We came up with bounds on rho. Rho was -4 to 4, and theta was 0 to 2 pi. Now, parameterizations aren't unique. There could be several ways to do it, but this is one that just kind of fell out when we were using spherical coordinates instead of cylindrical. And sure enough, we get the cone again. Notice it's been rescaled so that it just fits the box nicely, but you can force you can force Maple to keep everything in proportion by choosing scaling equal constrained. So now we've got the correct cone. The tip out angle here was pi 6, so it's kind of a taller than wider kind of cone.